Hi everyone. So I'm Chandra Shekhar from IIT Indore, and I'm going to be talking about the impact of light cone on the C2 and H1 21 centimeter signal statistics. So the problem that we want to deal with is to study the epoch of reionization, which is basically the era during which our universe got reionized from the radiation that was emitted from the stars and galaxies that were forming during this period. And what we plan to do is that we want to detect certain line emissions that might have originated from this cosmic era. So one of them is the 21 centimeter signal, which is emitted from the neutral hydrogen and is abundantly present in the early IGN. So it makes this a excellent probe of the IGN from the Earth. And the other line emissions like CO, C2, and O3 are emitted from the star-forming galaxies, which are just the ionizing sources, making them an excellent probe of the galaxies during the EOR. So now, before we go into, let's say, about how to interpret the results that we observe using these line emissions, so one must be careful about certain effects that might be inherently present within the observed signal that we finally obtain from observations. So since the signals happen to originate from different cosmic times along the line of sight, as we can see in this schematic, that is, if we have two different slices which are in the sky plane, and they are separated by distance along the line of sight. So it means that they are at two different cosmic times. And when they reach the observer at the same time, so what it means is that we are observing a 3D volume which consists of a series of such cosmic times in between. And it therefore definitely implies that the signal that we have observed is continuously evolving across the line of sight. So this phenomenon is known as the light cone effect, and therefore it impacts the observed statistics that we are interested in. For example, it could be power spectrum or bispectrum. So in the right hand side, we actually see some examples of simulated light cone slices. So the top one is from C2, represents a C2 signal light cone slice, and the bottom one is the 21 centimeter signal. And as we have explained, so this signal is evolving across the line of sight, representing different cosmic times. So therefore, what it means is that if we are to, let's say, estimate the statistics that we're interested in, we must consider this how this light cone effect actually impacts these statistics. So this is the goal of our study, and what we find is that the light cone effect has quite some impact on the power spectrum. So what we show here is the C2 power spectrum, and the light cone power spectrum is shown in the dashed lines, and is compared against the coeval power spectrum shown in the solid lines. So what we see is here is that for certain redshifts like 6.8, we actually kind of see a significant impact on the power spectrum, and it goes beyond 15%, meaning that one does need to consider light cone effects for the C2 power spectrum. Now, the other statistic that one might be interested in is the cross power spectrum, because that is a robust statistic. It has potential uses for parameter estimation. So now, before we come into the results of how light cone might impact cost power, so I just wanted to show the underlying reionization histories that we have considered for this study. So what this shows is the different evolution of the global neutral fraction with redshifts, and it basically represents three different cases which has different astrophysical parameters, and represent, as I mentioned, three different reionization histories, because as we are about to see, the impact of light cone on the crossbar is dependent on what kind of reaction history you're dealing with. Sorry. So in the right hand panel here, in the right hand side, what we see is the crossbar spectrum for these different reaction histories represented by H1, H2, and H3. So, and these solid lines over here represent the crossbar spectrum. And as usual, the dashed line represent the crossbar spectrum from the light cone cubes. So what we see is that for different redshifts and what kind of reaction history you're dealing with, this impact of light cone varies quite significantly across the reaction histories. And what we see is that particularly for reaction history H3, that the impact of light cone is very significant, up to 20% for redshift 6.4. This is and the reason for why we see such significant impacts on the crossbar is because light cone effect has a much more drastic impact on the 21 centimeter signal, and hence we see that reflection in the crossbar spectrum as well. So what we can just simply conclude from this is that crossbar is heavily impacted by light cone, and its impact is very much strongly tied to the underlying reaction history. And finally, what it implies is that since crossbar spectra has potential uses in parameter estimation, so therefore we must take the light cone effect into account for this case. Now, along this line, what else we can do to model the light cone effect? So one of them would be to consider, let's say, the presence of time evolving scatter. Now, what do we mean by that is, let's say we can understand by taking this example. So N gamma here represents the ionizing flux, which is responsible for reionizing the IGN. And a reasonable astrophysical model for this ionizing flux would be to assume that it is proportional to the star formation rate of the galaxy, and it is usually dependent, let's say, parameterized by the mass of the halo that on which the star in which the star formation is going on. But also there could be some scatter present in the relation between N gamma and SA part, so which is usually represented by a parameter which we represent by sigma, and it might so happen that the sigma is dependent on redshift, that is, it evolves with cosmic time, and whatever has a time evolution will definitely attribute its light cone effect. Now, what I'm going to show you is the impact of scatter on the bispectrum statistic, but without the time evolution. So before we jump into that, so we just quickly recap how bispectrum is estimated. So unlike the power spectrum, so we need to deal with three different K modes here, and we need to ensure that they form a closed triangle in the Fourier space. So to parameterize all of the unique triangles that we might form, so we define an angle alpha, which is basically the angle between the negative of K1 vector and K2 vector. And we also ensure these three conditions such that we have identified all of the unique triangles in the Fourier space. And we then use this equation. We take the ensemble average of the Fourier fluctuations for three different K modes to estimate the bispectrum with proper normalization. So now what I show you here is the different bispectrum for the cases where we do have scatter and in the case when we do not have scatter. So on the y-axis, we have the ratio K2 over K1, and on the x-axis, we have that angle represented by cos of alpha. So they just simply parameterize the shape of the triangle, whereas the value of the K1 represent the size of the triangle. So what we see here is the top panel representing the bispectrum of the 21 centimeter signal, when we just assume that a straightforward relation exists between the ionizing flux and SFR, and it is represented by the mean ionizing flux relation to the SFR. And on the second case, we have where we have introduced scatter in the relation. So now what we see is that we have some quite some impact due to the introduction of this scatter. That is, we can see that in certain pixels here, we can see that the impact is quite significant. So the ratio, the change delta B is, it could be twice that of the mean by spectrum. And of course, this result is for the scatter where it doesn't evolve with time. That is, yeah, a single sigma is present for all the cosmic times that we consider. So what we can do further along this line is that to deal with the light cone effect for bispectrum, we need to consider the time evolution of the scatter. So which means that things might get more complicated. So therefore, we need to carefully model that. And similar to the auto bispectrum, we can also consider cross bispectrum and the impact of light cone on this. So therefore, along with the impact of light cone, we also need to model the scatter so as to make a complete model of the statistics that we will be observing in the future. So with this, I would leave you here, and thank you for your time.